then in order to be able to implement and use convolutional neural networks, we basically need to understand those key components. So the key components, one of them is the convolutional layer. So it's basically the convolution that I told you plus activation. So this is what we call the convolutional layer. And they have some details that we are going to discuss together. After that, we need to just get the idea of pooling. So again, it's the same thing as I told you in that simple example, but you might need to know a bit of more details. And then finally is the output layer. So the output part, the output MLP, is basically what we had before. So there is nothing new about that. The only things that we need to know are these two parts, right? So how convolutional layers work and how pooling works, and what are the details in practice showing up, okay? So convolution is basically what I showed you. This is exactly the same definition. So if you're talking about convolution on image or data X, sample X, and then you have a particular filter W, then you can do it with a stride S, and out of it you're going to get another feature map, right? Now, in the example or in the previous slide, I told you that we have n by n matrix. In general, you don't really need to have n by n, right? You can have a rectangular matrix, right? And it doesn't change the fact that you're simply scanning it, right? You could also think about a rectangular filter, but I'm not doing it here because I have not seen in practice at all rectangular filters. But again, it does not change the fact that you're scanning by a small rectangular matrix, another rectangular matrix, right? That's okay. Yes, you had a question?
I was just saying, like rectangle is just like a square, but you zero out like the top.
Yes, yeah, you can always think like that, but yeah, people always think like it must be a because sometimes for the input image, you could have like different number of pixels for rows and columns. You can do it. It's not going to harm. And as you said, you can always pad as much as zeros that you want to just make it square, right? Yes?
In practice, do we usually have as greater than f or smaller than f? Or
What greater than f? Sorry?
S.
As typically smaller than f.
Within the margin of.
Yes, I mean, you can do that, but you are simply throwing away some pixels then, right? Because this is here, and then it jumps somewhere and some pixels in between are getting totally missed. Unless you know that they are useless, you typically don't do that.
I was thinking about like if S is smaller than f, some pixels will be like rescanned.
Yes, but actually the best case is when S equals by 1, right? So you don't care about rescanning. You don't want to miss anyone, right? But as I said, you are going to see shortly that you typically put S equal by 1. And whenever you want to do any stride, you're going to do it later by just resampling. I'm going to explain that. Basically, a stride is resampling, sampling from the data. OK, so that's going to be the convolution. So the expression is exactly as I told you before. So if you want to compute one particular part of that feature, you get your filter, you put it on the corresponding part of the data, and the corresponding part is this guy, right? And then you put it there. You just multiply all the weights inside the filter to that part of the data, and then you sum them up. This is going to be the value. Yes?
I'm just wondering, do we do the same thing if the x is in 3 dimensions, like the image of height of 3?
Yes, we talk about that. You mean multi-channel images,
yeah.
right? We're going to talk about that, right? Right now, you just think about 2D stuff. I'm going to add that one later. Yes?
Just for the index, so you have I minus 1 times, right?
Right.
I, like, it goes up to n number, right? Because it goes up to the entire frame.
Yes, then you should drop those last ones. Yeah, but we're going to see. We can pad 0 to get rid of that as well. So we'll talk about that, Norse. Questions? OK, so now let's just think about this case. So here I have 4 rows, 5 columns, right? So this is my data. And then my filter is 2 by 2. What I'm going to do, I am going to just put this 2 by 2 filter here, right? So I look first on a subpart of the input, which is 2 by 2, the first 2 by 2 subpart. I get the ASOP part. I multiply every single entry. So x11 gets multiplied with W11, right? x12 multiply with W12, x21 W21, x22 W22, right? Every single entry gets multiplied with the corresponding guy. You sum them up. This is one single number, right? You write down that single number here, right? This is your first feature. Now, you want to compute the next feature. Well, if you are doing it with a stride 1, so here stride is 1, I'm going to just shift everything 1 right, right? So this is going to go 1 right. Again, you see this part. You get this one. You multiply it with this guy. And then you write it down here, right? Everybody's clear, right? And you keep on filling out this whole matrix, right? Now, one thing that you can say if I do know what is the size of my filter, if I do know what is the size of my input, and if I do know what is my stride, I can simply compute the number of rows and columns that I see inside my output, right? Everybody agrees? Yes? So you can simply do it like this. So in the original slide, I put it here, but you don't really need to memorize anything. So this is what's going to be the number of rows you have inside Z, right? N minus F, because that filter is not going to let you go beyond something, right? And then divided by S plus 1, right? Now, this guy, this number here, as I said, you don't need to memorize the formula. The only thing that is important to have intuition about is the factor S, right? So if you increase the stride, like you make it 2, then the size is roughly getting half, right? If you make it 3, the size is roughly getting 1/3, and so on, right? And you can see it here. So here you can put it inside the formula. If you put it inside the formula, you're going to see that, well, you have 3 rows, 4 different columns. But as I said, you don't really need to memorize the formula. You can always look at the filter input, think about this stride, and then you can simply do the calculation if you need, right? Everybody's clear? Questions? Okay, so now just let's do one numerical example. So say this is my filter. So my filter has the weights 1, 0, 1, 1, right? So these are the weights inside my filter, right? Now, yes?
I was going to ask, is there, the smaller the filter, the smaller the weight matrix, right?
The smaller the filter, the smaller weight matrix, right? I mean, filter is the weight matrix.
Well, I mean, the less pixels you scan at a time.
Yes, exactly.
Is there an advantage or disadvantage versus going to scanning more at a time and having more weights versus scanning less at a time and having less weights, or it doesn't matter?
It depends. I mean, again, you're going to see the number of weights that we have inside this filter is essentially the number of parameters that we have. Now, if you want to increase the capacity of your model, you need to increase the number of weights. But do we increase the number of weights inside one filter? No, we don't do it. We just increase the number of filters that we have. Because we are not going to do it with one channel. We are going to do it with multiple channels. Now, if you want to increase, you just increase the output channels, right? But, yeah, I mean, in practice, you always have like 5 by 5, 7 by 7, at most 9 by 9 filters, not more than that. No. Okay? So, now, this guy is the filter 1, 0, 1, 1. Okay? And these guys are the ways that I want to just scan or convolve it with this image. So the first time I'm going to get this guy and put it here, right? And when I put it here, 1 gets multiplied with 1, 0 gets multiplied with 0.9, 1 by this guy, another 1 by this guy. So if I add them up, it's going to be 2.1, right? Now, if I'm doing it with a stride 1, you know that this filter is going to just shift 1 right, right? So what's going to be the number coming out of it? If like, what would be the next number inside the feature map, inside the green map? What is it? 1.1, right? It should be 1.1. No? Everybody agrees? You see that? Moment of truth? Yes, it is 1.1. Yeah. Okay. So again, this guy gets multiplied with this one, then it goes here. The next one is going to be 2.1, right? And you keep on going like this, right? Everybody sees what we are doing, right? You get the idea how the convolution is going on, right? Each time you put this guy on one part, and then you exactly multiply the weights to that, you add them up, you get those numbers, right? Everybody's cool? So this is going to be the feature map when I do it with a stride 1, right? What if I do it with higher strides, say, for example, stride 2, then basically it only changes the jump that I do, right? So for example, here, the first submatrix that I'm going to scan is this 2 by 2 matrix, right? So I get this one, I multiply it to those weights, and then I write it down here. What would be the next submatrix? It's going to start at x1, 3, right? And then it goes to x1, 4. So this is going to jump here, right? And then you do the multiplication, you write it down here. Where should I go next? I should go down, right? Because if I want to just jump by 2, this filter gets out of the input, right? So I cannot do it. I'm going to jump down, right? So I'm going to jump down. I come here. Then this is going to be z. Again, the next z, and it's over, right? Yes?
With the stride, we completely omit like the last column.
Sorry,
We completely skip the last column of x.
Yes. Here we completely skip the last column of x, but we're going to figure that out. I mean, we can pad 0, yeah, and then we're going to get rid of that. So we talk about that. Okay, so yeah, that is the case. And now, again, you can compute the number of rows and columns you have, right? And if you do that, then, well, it's 2 and 2. And you again see roughly that z as compared to the case with stride 1, roughly, not exactly, roughly shrunk with size 2, right? Because you just doubled your stride, right? So, again, same numerical example. Now we want to just do the convolution with the stride 2. So this is going to be the first part. We had 2.1. The next part is going to get this one, and then it's going to just scan the next part of the input, but it's going to jump it with step 2, right? So this is going to be this part, right? And it's again 2.1. This guy is 1.7, 2.5. This is your output feature, right? This is the z coming out of your convolution. Everybody's clear? Questions? No question? Okay. So if you got no question, then I have a question. Looking at the thing we got out of, we had this exactly same input, right? So the blue matrix, the blue map, did not get changed. Or filter was also the same. So filter also did not get changed. The only thing that we changed in this example as compared to the previous one was the stride, right? In the first one, stride was 1. In the second one, stride was 2, right? Now, looking at this one, looking at these two, can you tell me if there is any connection between this bigger map and the smaller map? Go ahead. Any idea?
You cut off the second row.
Exactly.
The second, fourth column, and then the second row.
Right. If you remove these ones, if you remove these rows and columns, then you're going to end up with this one, right? So what you see here is actually when you get the output with a stride 2, essentially you get the output with a stride 1 when you downsample, right? And by downsampling, what do I mean? Simply I mean that if I say downsampling by factor f, it means that for every column, I keep the first column, I just drop f minus 1 columns, right? And then I go for column f plus 1. Again, I drop the next f minus 1, and so on, right? And for the rows, I do the same, right? The first row I keep, the next f minus 1 rows I'm going to drop, then I keep the row f, and so on, right? So here it is a downsampling with factor 2, right? I keep the first column, second goes. Third column, fourth goes, right? Again, the first row remains, second goes, third one remain, right? Everybody's clear? So what you have with the stride 2 is just downsample version of stride 1, right? And what is the factor of downsampling? It's exactly the stride that you're doing the convolution with, right? So now, just to make sure that everybody got the idea of downsampling, so if this is your original map and you want to do the downsampling, then this is the case when I do downsampling by factor 2, right? Everybody's clear? Yeah. What if I do with factor 3? Then I'm going to keep the first one, drop the second and third. Keep the fourth one, fourth one, drop fifth and sixth, and so on, right? So this is going to be factor 3, right? And you can keep on going like that, right? Everybody's cool, yes? So now, moral of the story, when I am doing convolution with higher stride, I'm basically doing downsampling. So it means that I can think of the convolution of filter W with data X. When I do it with the stride S, I can think of convolution with the stride 1, right? Same convolution with the stride 1, which has been downsampled by factor S. Everybody's clear? Questions? If I think about convolution with the stride S, so here is convolution by stride 2. I could say instead that I'm not doing convolution with the stride 2. I could say I do the convolution with the stride 1 first, and then I downsample with factor 2, right? That's the same thing. Yes? Sorry, I didn't hear.
Oh, instead of downsampling, can we like kind of expand, like replicate like those pixels so that we get more information?
Replicate those. Oh, then you are. Oh, replicate. Why we should replicate?
Like if we expand, like replicate, we get like more information.
Oh, you're talking about upsampling then, right? And not replicate necessarily. I mean just adding 0 in between so that it just expands, right? We're gonna do that. Don't worry. This is downsampling, right? So we are losing information here.
Oh, that trains the model better.
Sorry?
And that trains the model better.
No, it doesn't. It just reduces the complexity.
Oh.
Yeah. I mean, you usually do it very late. You don't do it at the beginning. But what you are thinking about is to just add more, somehow expand the image, for instance, so that I extract more information. That is upsampling. This is the next thing we talk about.
Oh.
Yeah. Is it clear? So, yes.
I didn't get it. So if you do convolution X with W with 1,
Yes.
you should get a 2 by 3 matrix. Because the width of the filter is 2, right? So the first time you scan you get 3.
No. Just look at it here. This is the case. This is the example we did, right? So this is how we did the convolution,
yeah,
right?
You see here when you have 5 columns, you reduce by 1.
Right.
Because the width of the filter is 2.
Exactly. When you are doing with the stride 1, you're going to reduce with f minus 1, right?
Yeah. So in your formula, when you so the input of downsample is already reduced by 1.
Yeah, but that is a tiny one. It's not reduced in scale, right? So you don't get half. It's just 1 column or 2 columns. At most, you're losing f minus 1 columns and rows. We're going to get rid of that issue as well. We do 0 padding later. Yeah. But I mean, if you do 0 padding, you can make this guy exactly the same size as this one, right? But you are not losing in terms of scaling. So it means that you don't get like 4 by 4 or say 100 by 100 and then it shrinks to 50 by 50, right? It's going to be 98 by 98. It's okay, right? No? Yes?
Yeah, so in practice, do we always prefer stride 1 than other higher stride? Because for other higher stride, you lose information, right?
Yes. I mean, in practice, we usually do it with the stride 1 initially, right? And whenever we feel like we are having too much information, then we do pooling with higher stride. This is what we do in practice. But right now you can think in general, okay, maybe you are at one position where you prefer to do it with some stride, and what is the reason we're going to see it later. No? Yes?
What do you, is the weights in the filter mean anything? Like, does that emphasize any different like pixels? So if I use, for example, like this diagonal 0 and this diagonal 1, I'm going to get like a different feature map. So what is there any logic to choosing the weights in the filter?
Oh, we're going to learn the weights. Weights are the parameters that we are going to learn. So yeah, it's just an example here. Later on, I mean, we're going to keep it W1, W2, W3, W4. We compute the gradient backpropagation, and then, yeah, these are the things that we are going to learn, right? These are the parameters. But right now, I just want to give you the operation clear, right? So I think they made this air conditioning device working like, because I don't hear anything. And I know I'm not good at hearing, but this one is just making things more, yeah. So sorry if I am just a bit too much weird today, so not my fault. Okay. So I know I'm getting old, so it works not working very well, but not that bad. I mean, within a few days. Okay. So yeah. Now, right. Okay. So we are here. So basically, what we do by a stride, any stride, is basically doing downsampling. Because of that, we can simply think of doing the convolution always with the stride 1. Okay? That's going to be much easier. Instead of thinking about the stride, you always think that you are doing it with a stride 1, right? And whenever you want to just increase your stride, you basically get the output and you downsample it. Now, there are a couple of reasons that we think like that. So why we always think like a stride more than 1, why we should think of it like as two different operations, convolution plus downsampling. There are two main reasons. One of them is that you're going to make the backpropagation significantly easier. So you're going to see that basically you need to always backpropagate over a convolutional layer with the stride 1, and then those resampling again in the backpropagation is going to be resampling again, right? So it's going to make backpropagation significantly easier. You're going to see it. But there is one other reason for that. And the reason is roughly the same thing your friend asked, is to just do the convolution with the stride less than 1. You are now able even to do convolution with the stride less than 1. What do I mean by that? So what is convolution with a stride less than 1? Say I have this guy, right? This is a 3x3 map, right? Now, for some reasons, I don't like a 3x3 map. I want to expand it. How can I do it? I can do the reverse operation, with what we call it upsampling. It means that I look at every single column and row, I just add zeros in between, right? So here I'm doing it by factor 2, right? If I want to make it larger, then I just increase the number of columns and rows, right? Everybody's clear? So this is being the upsampling. And now, instead of giving this original image, 3x3 image, to my convolution, I can simply give the upsampled one, right? And by giving the upsampled one, the thing that is going to happen is that at the output, I am getting more features, right? So what is happening here is that, for instance, say I have a filter which is 2x2, right? If I put my filter here, first it's going to look at these first 4 pixels, right? Then it goes for the next one, it looks into these second batch of 4 pixels, right? Whereas if I look here and I do this scanning, then my filter is going to look at the first pixel, then second pixel, then third pixel, and so on, right? So my filter gets the chance to just look at every pixel individually, right? And this might be a better idea initially because I want to process every pixel independently, right? So this is giving me the opportunity to increase the size and process every single of them independently, generate larger and more informative feature map, right? And if I do that, this is basically what I'm doing with stride, but here we are doing it with a stride less than 1. So when you are doing with a stride 1, you just get your filter and then you just jump by factor 1 each time, right? If you do it by stride 2, you get your filter, you jump by factor 2, right? Now, if you do it with stride half, this means that you put it here, right? Again, you put it here, then you go for the next one. But when you put it here and again put it here, you add zeros in between, right? And what does it mean? It basically means that you first do upsampling and then you do the convolution. So this is the idea of convolution with fractional stride. And basically what you do in the convolution by fractional stride, you get your original image. You do it you do the upsampling by some factor, and then you do a convolution with the stride 1 on that one. If you do that, this is what essentially we call it stride by factor 1 over exactly the upsampling factor. So if I talk about a stride with factor s, which is smaller than 1, I simply mean that, say, for example, s is 1/2, right? So it means that I first upsample with factor 2, and then I do the convolution. This is basically the convolution with factor 1/2, and we can just think about like smaller than 1 strides. Questions? Yes? Oh, that is not important in zero. I mean, I get what you say. You said, like, for example, I just replicate exactly the blue pixel here instead of putting 0. You can do that, but basically your convolution is doing that for you because that is a linear operation, right? So this is going to happen in your next feature, right?
I'm thinking like the filter we were using, for example, using an L, isn't it kind of like detecting that kind of edge? So if it's at this point it's just seeing 1 pixel, then I'm not really seeing an edge because all the others are zeros. So right now I'm kind of creating an edge.
Yes, that's fine, but the key point is that like your filter goes over 1 pixel individually, right? And then the next time is going to go over 1 other pixel. I mean, this is not the best example, but if you think about a more wider image and a larger filter, then you see that your filter gets the chance to just process everybody independently. Like, for example, this, think about the yellow one, right? First time, if you are doing it with the stride 1 on that image, then you go over everything, and then you come down, right? Once you come down, you're going to scan that yellow one with your lower down weight, right? And then you finish that row, you again come down, now you start to, scan that one with your upper left weight, right? So every single pixel gets this chance to get multiple times processed by different weights, right?
Different neighbors. Okay.
Yes. And then somehow that idea of interpolating is happening in the output directly. So you don't really need to think about that. But if you do that, you are not going to lose anything. Because it's a linear operation, on linear operation, same thing, right? Questions? Yes? Yes?
What's the advantage of doing this as opposed to reducing the size of the filter or doing 1 pixel at a time?
Yeah. Because this is the point I was trying to make. So if you think about this guy, right? If you reduce your filter size, right? So you're not increasing the number of times that particular pixel is being scanned, right? Whereas if you keep that fixed and you increase your image size, then the number of times that pixel is being scanned is increasing, right? And it's being scanned independently, which means that you're just looking at this pixel from different perspectives, right? So just think about this yellow one, right? When you start first, I mean, you finish your first row, then you come on the second row, and the first time, this guy is going to get scanned by the lower left weight, right? Then you finish this row, you come here again, then you scan it by the upper left weight, right? And same thing happens like this guy, the pink one in the center, is getting scanned so many times, and each time by a different weight.
The ones on the first row and first and last row.
Yeah, but you can simply add 0 around, right? And then if you do that, then the same thing happens to them, right? Yeah? Make sense? Yes?
So, without using upsampling, we can actually use S that are smaller than 1?
Yeah, basically what you do is doing this one again, right?
So only in this case we use like S smaller than 1.
Yes, when we say S is smaller than 1, that S should be exactly 1 over something, right? And that 1 over something would basically tell you what is the upsampling factor. So if you say S equals by, I don't know, 1/8, simply means that you first upsample with 8, factor 8, and then you do the convolution.
Because I was wondering how does it work when we have S equal to 0.5?
S equal by 0.5. You just upsample by factor 2.
When we not doing upsampling.
Oh, you can show that this is, like you can write down the equivalent operation on X. But that is getting a bit more complicated. This is why I define upsampling. You can define that. It's not impossible.
So is this still the same to as you would want, or it's double?
Yeah, no, it's like you keep your filter on the first part, right? Once you scan with one part of it, another time you scan with another part of it, then you move. It's going to be the same thing, yeah? Yeah, you just put a mask on your filter each time, right? Which are those zeros, yeah? But you can just simply do it this way. Yeah, yeah.
So how are the value of the gray squares, the value of them be determined? Like
Value of, sorry?
So how will the value of the the gray squares, like the in between the
These guys, they're zero. They're zero. You don't need to do anything. I mean, it's gonna get taken care of later on, right? So because when you do linear process on it, your output is going to be non-zero, right? And it's eventually a linear combination of things. So you don't really need to worry about that. You just add zeros. Questions? No question? Okay, so yes.
If we do upsampling by a factor of 2 for an
Okay.
image, and then do downsampling for the same factor,
Yes.
we're getting the same. We're getting the same image, right?
Not exactly the same thing, I guess. Let me think.
We first do up and then down.
I guess so. I guess, yeah, it's gonna be the same thing, right? Right.
Okay.
So you can just do the convolution with stride one.
Okay.
Yes. Yeah. No worries. So, questions? So in general, you can think about general S, which is like any fractional number, right? 2/3. What does it mean? 2 is the downsampling factor. 3 is the upsampling factor. It means that you first go ahead and do upsampling with factor S1, which is the denominator, and then you do the convolution. After doing the convolution, you do downsampling with factor S2, right? Now, in practice, we don't get into those weird convolution strides, but if you really want to do that, then that is basically this. So there's no complication there. So moral of the story is that a stride is nothing but resampling, right? So whenever you talk about a stride, you basically do convolution with stride 1, and then you resample the output, right, or the input. And the key points that you should pay attention is that upsampling is always happening before convolution, right? Because you want to add zeros and process it. If you get the output and you do the upsampling, you just add zeros in between, right? And by doing that, you just add zero information. That is nothing useful, right? Same thing with downsampling. This should always happen after your calculation, right? After the convolution. If you do it before, then your convolution simply loses the information, right? So the order is important, but rather than that, resampling is stride is nothing but resampling. Now, this way of looking at this stride is going to help significantly when we do backpropagation on the convolutional layers, and we're going to see